Hey everyone, so have you ever felt like work and energy in physics is just needlessly confusing? Or maybe the math problems just never seem to click? Well, you're in the right place. In this explainer, we're going to break it all down, make the concepts totally clear, and the problems actually pretty simple.
All right, so here's our game plan. We're going to start with what work really means in physics. Then we'll build on that with the super important idea of angles. After that, we'll see how energy is the fuel that makes it all happen. We'll even uncover an unbreakable law of the universe, and we'll finish up with the true meaning of power. Ready? Let's dive in.
First things first, what is work? You might think you're working hard studying for a test, but physics has a very different and way stricter idea about what counts.
You know, in everyday life, we say we're working when we study for hours, or even just stand still holding a heavy bag. But physics is picky. For work to be done, there are two rules. You have to apply a force, and that force has to actually make something move. So pushing a box, swimming, lifting a weight, that's work. If nothing moves, it doesn't matter how exhausted you get, you've done zero work.
So, here's the bottom line. Work equals force times displacement. Just imagine you're pushing against a giant boulder with all your strength. You're sweating, using all your muscles, you're applying a ton of force. But if that rock doesn't budge an inch, in the eyes of physics, you have done exactly zero work. It's tough, but that's the rule.
Okay, now for the secret ingredient. This is the piece of information that makes everything else make sense, but it's often kind of glossed over. It is all about the angle between your force and the direction of movement. Trust me, this changes everything.
So it turns out that first formula was kind of the light version. The real formula is force times displacement multiplied by something called the cosine of the angle between them. We usually write that angle with the Greek letter theta. This little addition is the key because it tells you how much of your push or pull is actually helping with the movement.
Now don't worry, you don't need to suddenly become a trig expert. For pretty much every problem in this chapter, you just need to memorize these three values. If the angle is 0 degrees, the cosine is 1. If it's 90 degrees, it's 0. And if it's 180 degrees, it's -1. That's it. Let's see what these actually look like in the real world.
First up, the easy one, positive work. This is what happens when the force you're applying and the direction the object moves are lined up perfectly. The angle between them is 0 degrees.
Let's bring in our good friend Chintu Lo. He's pushing a box. His force is pushing forward, and guess what? The box moves forward. The angle is 0, and the cosine of 0 is 1, so the work is just force times displacement. It's positive, it's simple, it's exactly what you'd expect.
Okay, next up is zero work. Now this one can feel a little weird at first. This happens when the force you apply is at a 90-degree angle, completely perpendicular, to the direction of the movement.
So imagine Chintu Lal is now working as a porter at a train station. He picks up some luggage. To hold it up, he has to apply a force upwards, right? Fighting against gravity. But then he walks forward. So the force is vertical, but the displacement is horizontal. That's a perfect 90-degree angle. And what's the cosine of 90? It's 0. So the work done against gravity while he's walking is a big fat 0.
And finally, we have negative work. This happens when the force is acting in the exact opposite direction of the displacement. We're talking a 180-degree angle here.
Chintu Lal is cruising in his mighty Lord Alto, and suddenly he has to slam on the brakes. The force from the brakes is pushing backward, trying to stop the car. But the car still skids forward a little bit before stopping, right? So the force is backward, but the displacement is forward. They're in opposite directions. That's 180 degrees. The cosine of 180 is -1, which means the brakes are doing negative work on the car.
So if work is something that gets done, what pays for it? Well, the answer is energy. You can think of energy as the currency you spend to do work. They're really just two sides of the same coin. And what's interesting is they're both scalar quantities, which is just a fancy way of saying they have a size, like 10 joules, but they don't have a direction. It's just an amount.
The two main types of energy we're going to focus on are kinetic and potential. Kinetic energy is the energy of motion. Think of a moving car, a flying baseball. If it's moving, it has kinetic energy. The formula is 1/2 times the mass times the velocity squared. Potential energy, on the other hand, is stored energy. It's the energy an object has because of its position, like a book sitting high up on a shelf. Its formula is mass times gravity times height.
But wait, where did that crazy-looking kinetic energy formula even come from? It's not magic, I promise. It's actually derived directly from the definition of work. If you follow along here, you can see how we start with our basic work formula, then we just sub in a few other classic physics equations we already know, and by the time we get to the end, assuming the object started from a standstill, look what happens. The work done is exactly equal to 1/2 mv squared. The work you do is literally what becomes the kinetic energy.
And this idea leads us to one of the biggest, most important rules in all of science, the law of conservation of energy. It's a simple but profound idea. Energy cannot be created, and it can't be destroyed. It can only ever be changed from one form to another.
Let's watch this unbreakable law in action with a simple falling ball. Okay, picture a ball being held at its highest point, just before it's dropped. It isn't moving yet, so its kinetic energy is 0. At this moment, all of its mechanical energy is stored up as potential energy, just because of its height.
Now we let go. As the ball falls, its height gets lower, so its potential energy starts to decrease. But where does that energy go? It doesn't just disappear. It transforms into kinetic energy as the ball starts moving faster and faster. Right at the halfway point, it's a perfect 50-50 split. But here's the key. The total amount of energy has not changed one bit.
And then, just the split second before the ball hits the ground, its height is basically 0, so its potential energy is all gone. Where is it? All of that stored potential energy has been converted into the energy of motion. It is now 100% kinetic energy. The total amount of energy stayed the same the whole way down. It just changed its outfit.
All right, last topic, power. In physics, being powerful isn't just about being strong. It's not about how much work you can do, but about how fast you can do it.
Power is simply the rate of doing work. The formula couldn't be easier. Power equals work divided by time. So check this out. If Chintu Lal and his friend Mintu Lal both do 10 push-ups, meaning they do the exact same amount of work, but Chintu does them in 10 seconds and Mintu takes 20 seconds, Chintu is actually twice as powerful. And the unit we use to measure power is the watt.
Let's put this into practice with a quick problem. We've got a crane lifting a 500-kilogram load 10 meters high, and it does it in 20 seconds. So, step 1, calculate the work. That's just the potential energy it gained, mgh. We'll use 10 for gravity to keep the numbers round, and we get 50,000 joules of work. Step 2, time taken. The problem tells us it's 20 seconds. Step 3, apply the power formula. We just divide the work by the time. 50,000 divided by 20, and boom, step 4. Our final answer is 2,500 watts. See? Not so bad at all.
And that brings us to a final thought. We've learned that in physics, power is all about speed, the rate at which you get things done. Which kind of makes you think, doesn't it? In our own lives, outside of the classroom, when is it more important to be fast and efficient than it is to just be strong and persistent? Something to ponder. Thanks for joining me.